Bayesian decision theory. We discuss probability theory as the framework for making decisions under uncertainty. In classification, Bayes' rule is used to calculate the probabilities of the classes. We generalize to discuss how we can make rational decisions among multiple actions to minimize expected risk. We also discuss learning association rules from data. Introduction. Programming computers to make inferences from data is a cross between statistics and computer science, where statisticians prove the mathematical framework of making inferences from data and computer scientists work on the efficient implementation of the inference methods. Data comes from a process that is not completely known. This lack of knowledge is indicated by modeling the process as a random process. Maybe the process is actually deterministic, but because we do not have access to complete knowledge about it, we model it as random and use probability theory to analyze it. At this point, it may be a good idea to jump to the appendix and review basic probability theory before continuing with this chapter. Tossing a coin is a random process because we cannot predict at any toss whether the outcome will be heads or tails. That is why we toss coins or buy lottery tickets or get insurance. We can only talk about the probability that the outcome of the next toss will be heads or tails. It may be argued that if we have access to extra knowledge such as the exact composition of the coin, its initial position, the force, and its direction that is applied to the coin when we tossing it, where and how it is caught, and so forth, the exact outcome of the toss can be predicted. Exactly pieces of knowledge that we do not have access to are named the unobservable variables in the coin tossing examples. The only observable variable is the outcome of the toss, denoting the observables is by z and the observable as x. In reality, we have that x is equals to f of z, where f dot is the deterministic function that defines the outcome from the unobservable pieces of knowledge. Because we cannot model the process this way, we define the outcome x as a random variable drawn from a probability distribution p of x equals to little x that specifies the process. The outcome of tossing a coin is heads or tails, and we define a random variable that takes one of two values. Let us say x equals to 1 denotes that the outcome of a toss is heads, and x equals to 0 denotes tails. Such x are binarily distributed where the parameter of the distribution p0 is the probability that the outcome is heads. That is, p of x equals to 1 is equals to p0, and p of x equals to 0 is equals to 1 minus p of x equals to 1, which is equals to 1 minus p0. Assume that we are asked to predict the outcome of the next toss. If we know p0, our prediction will be heads if p0 is greater than 0.5 and tails otherwise. This is because if we choose the more probable case, the probability of error, which is 1 minus the probability of our choice, will be minimum. If this is a fair coin with p0 equals to 0.5, we have no better means of prediction than choosing heads all the time or tossing a fair coin ourselves. If we do not know p of x and want to estimate this from a given sample, then we are in the realm of statistics. We have a sample x containing examples drawn from the probability distribution of the observables x to the t, denoted as p of x. The aim is to build an approximator to it, p to the head of x, using the sample x. Now, in the coin tossing example, the sample contains the outcomes of the past n tosses. By using x, we can estimate p0, which is the parameter that uniquely specifies the distribution. Our estimate of p0 is p0 head equals to the number of tosses with outcome heads divided by the number of tosses. So numerically, using the random variables, x to the t is 1 if the outcome of toss t is heads and 0 otherwise, given the sample heads, tails, heads, tails, heads, tails. we have x equals to 1, 1, 1, 0, 1, 0, 0, 1, 1, and the estimate is p0 hat equals to the summations of x to the t, summing for index t starting from 1 to n, then divided by n, which is 6 divided by 9.